Hello everybody and welcome. My name is Hamza Hadri and I am a PhD student at University Hassan II, and I will present our paper named Semantic Segmentation using MSRF-NET for ultrasound breast cancer, which was our submission to the 22nd International Conference on Intelligent System Design and Applications. First, First things first, deep learning stands out as one of the most state-of-the-art modalities in the search for a reliable method to classify or segment breast cancer. All started with the introduction of the famous UNet architecture, which demonstrates formidable results and consider reference in biomedical image segmentation. In the same context, another model showing great results in many biomedical image segmentation is the MSRF-NET, or Multi-Scale Residual Fusion Network. This architecture takes advantage of many mechanisms in the field of deep learning and can be separated to four separate elements: encoder, MSRF subnetwork, shapestream, and decoder. The first element is the encoder, which use four separate blocks, each contain convolution layers followed by squeeze and anti-excitation block. Moving forward to the MSRF subnetwork that represent the core of the MSRF network. The subnetwork contains several DSDF blocks, dual scale dense fusion. A single DSDF block have two streams, one for the high resolution and the other for the low resolution, with the application of successive convolution and leaky activation layer. In a nutshell, MSRF subnetwork responsible for capturing composite feature map by combining low and high resolution in the DSDF block, consequently improving the image segmentation. In MSRF-NET, a gated shapestream was used. It is responsible for detecting the boundaries of segmented objects and passing this information into the network. This element gives the model the capabilities of segmenting objects of various sizes. The final element of the model is the decoder. The decoder block from D1 to D3 employ two different attention structures. The first one is a gated attention and the second one uses spatial and channel-wise attention. Now, after we give a brief description of the MSRF-NET, let's present the implementation. TensorFlow and Keras API was our way to go in implementing this architecture, mainly for its simplicity. Moreover, we use an open breast ultrasound dataset. These 320 grayscale images in this dataset are initially normalized to 120H by 120H in size. Additionally, a 10 years experienced radiologist identified the tumor region. To ensure an objective benchmark, we use 10-fold cross validation, 80% for training, 10% for validation, and the same chain for testing. In semantic segmentation, we can adopt different quantitative measures. In general, they are all calculated from the four metrics of the confusion matrix. Our evaluation will use the task coefficient score or DCS, a recall, precision, and specificity. The evaluation process investigates the effect of various batch sizes on training and testing with two epoch sizes, 100 and 200, and equally important the learning age and image input size and their influence on the result in terms of convergence and performance gain. The first step in our benchmark process examines the impact of variable batch sizes on training and testing. The experiment demonstrates the effectiveness of small batch sizes with two performing the best with 93.9% in DCS and 32 performing the worst with 91.8%. Besides, as long as we augment the batch sizes, the training tends to be unstable. Additionally, a bigger batch size takes more time to train. Furthermore, we experiment with three input sizes: the original size of the image and size ratio of 1 to 2 and 2 to 1. The result exposes the low impact of input size on the overall performance. For example, the DCS shown only 1% variation, and time to train the model increased substantially. The 64 by 64 input size trained in 15 minutes and 256 by 256 in 38 minutes. In this slide, the first table presents the outcome of training in the network with 200 epochs using distinct path sizes. The DCS in validation increased, for example, to 97.9 in training, while he declined in testing. In testing phase with 93.5, indicating a high variance problem. Moreover, the validation metric does not increase after the 127 epochs. The learning rate plays an essential role in identifying the optimal model. The 0.301 learning rate converged fast after only 2 epochs. However, we could only achieve a DCS of 92.4%. A more significant learning rate takes substantially more iteration to converge. So we run the model for 200 epochs to ensure a fair comparison. In brief, the validation metrics for the second convergence for the second learning rate converge to 93.4 after the 147 epoch. However, in testing, the performance decline. This is the result of the high number of iterations product a high variance model. To illustrate the performance of the MSRF-NET, we compare with three widely used architectures, the famous UNet and its variants UNet++ and VNet. We use the same environment as the MSRF-NET to implement these methods. Overall, the MSRF-NET outperformed the three architectures in DCS, specificity, and precision. Furthermore, the MSRF-NET surpassed significantly the three architectures in frame per second, which could be beneficial for real-time application. In this work, we propose the implementation of MSRF-NET for ultrasound breast cancer segmentation, the multi-scale future fusion through MSRF sub-network, and the dual-scale dense fusion or DSDF blocks enhance the map feature exchange. Therefore, we achieve a competitive result in evaluation metrics and outperforming the three comparative structures. The outcomes support expanding the use of the MSRF-NET for other ultrasound breast cancer datasets and take advantage from the different elements in the architecture and improving them further. And thank you for watching this video and have a nice day.